Okay, so we're moving into direct variation today, which is a special type of linear function. So some linear functions qualify as direct variation. So how do we know when a linear relationship, a linear function, is a direct variation? So when a linear equation is written in standard form, let's be reminded what we mean by standard form. I told you we got to start learning all of these forms for linear functions. What does standard form look like? AJ?
Or it's like ax plus by equals c.
Yeah, ax plus by equals c. The x's and y's are together on the one side of the equation. The constant c is on the other side of the equation. So when a linear equation is written in standard form, and the c value is 0. So this is important. When our c value is 0, it is a special linear relationship called direct variation. So what that really means is, remember x is in control, it's the independent variable, it's the input, so and the output is our dependent variable y, so we say y varies directly with x. In other words, it is directly affected by what you do with x. Nothing else affects the situation, only the input. So basically, what happens then is rather than rewriting it in standard form, it has its own special form, and it looks like this: y equals kx. In other words, the function rule, you're multiplying the x value by something, but there's nothing else going on. There's no addition and or subtraction going on also. So y varies directly as x. That's what direct variation means. And k is called a constant of variation. So that's the multiplier on the x, our k value, also known as the constant of variation. So let's explore a situation that might possibly be one of these special linear relationships called direct variation. If there are 5 people in the room, each are wearing a pair of shoes, what would the total number of shoes be? If there are 5 people in the room, each wearing a pair of shoes, how many shoes, individual shoes, would there be in the room? Austin? 10. And how'd you get that?
There's 5 people and everybody has 2 shoes on.
Yeah, so basically a pair of shoes is 2. So if there's 5 people, 5 times 2 gives us our 10. Well, if there's 10 people, how many shoes would there be? 20, because we would take 10 times 2, and we would say there's 20 shoes. How about if there's 15 people? 30. So every time we are just taking the number of people times 2 to get our number of shoes. So we would say the total number of number of shoes in the room varies directly with the what? The number of shoes is the direct result of what? What happened in all 3 of those situations? The number of shoes was the direct result of the number of people that were each. The only thing that changed every time, in other words, was the number of people. So we would say the total number of shoes in the room varies directly with the number of people. So you tell me how many people are in the room, I can tell you how many shoes are in the room. Each time we multiply the number of people, as you just said, AJ, we multiply the number of people by 2 to get the total number of shoes. So how would we represent that as an equation? In other words, the equation would represent any number of shoes based on the number of people. 2x, okay. What's that equal? Y. Our total number of shoes, y, is directly affected by the number of people, and to get that total number of shoes, we multiply it by 2. So the number of people by 2 multiplied by 2 gives us the number of shoes. So what's our constant of variation then? What would we say our K value is? 2, yeah. Our constant of variation is 2. Every time that stays 2. Well, what if there were 2 extra pairs of shoes sitting in the closet? I always threaten that I'm going to throw some extra shoes in my closet back there in case I don't like the comfort level of the ones I'm wearing that day. So if I have a couple pair of shoes thrown back there in the closet, would it still be a direct variation?
Because they're not worried.
Yeah, but you're adding, it's so many direct variations, you just add it.
You're adding shoes but not people.
Because there's no people, so it'd just be like y equals 2x plus the amount of shoes.
So in other words, I wouldn't be able to say to you, tell me if let's say you didn't know those shoes were back there, would you be able to tell me how many shoes are in the room?
Yeah.
If I say how many shoes are in the room, if there are 11 of us here today,
22.
you would say there are 22, right? Based on if the number of shoes varies directly with the number of people. But what if I say, oh, you're wrong, I have a couple pair back there in the closet. Now, is it still direct variation? Does the number of shoes in this room vary directly with the number of people? No, it doesn't. So you're right. When we have to add that 4, we no longer have a C value. So in other words, wouldn't our equation look something like this then? Y equals 2x plus 4.
Yeah.
Okay. If we put this in standard form, how would we get this in standard form? Subtract 2x from both sides. We'd have y minus 2x equal to 4. In other words, the x's and y's would be together over here. We could just rewrite it like this, couldn't we? And what has to be true for a direct variation? When an equation is written in standard form, what has to be true? C has to equal 0. Does C equal 0 in this one? No, C equals 4. C does not equal 0. So we would say this is not a direct variation, okay? Not a direct variation. Once we throw in that extra pairs of shoes that have nothing to do with the number of people, nobody's wearing them in other words, we no longer have a direct variation. We cannot count on just being able to say, well, there's this many people times 2, so there's this many shoes. C is equal to 4, not 0. It throws it off. So that's just an example of when would we have a direct variation, when would we make it into just a linear relationship that is not considered a direct variation. Questions at all? Okay, let's go to the back side then. One of the things you will be doing in your homework is determining when in a set of ordered pairs represents a direct variation relationship or not. Let's be reminded what helps us determine if it's linear or not from a table of ordered pairs. What helps us determine if it's linear?
It goes up or down by some.
And what's it?
The difference between the x and y values.
The difference between the x and y values? In other words, do we find the difference between them? Or do we find the difference between each of the x's
Yes.
and the difference between each of the y's? And they both have to be a constant. So let's just check this out to see if it's even linear. So do this with me. What do we have to do to get from 2 to 4?
Plus 2.
Add 2. What do we have to do to get from 4 to 5? Plus 1. What do we have to do to get from 5 to 8?
Plus 3.
Oh no, does that mean right now then we don't have a direct or a linear relationship? It almost seems like it, doesn't it? But let's check out those y's. Let's see what's going on down there. 6, 12,
Plus
plus 6. 12, 15, plus 3. 15, 24, plus 9.
If you divide them all by 3, they have the same amount as the top.
You divided them all by
The
3.
bottom
All
ones.
the y's by 3. You would get the the change in x.
Yeah.
Okay. So right now it's looking like it's possibly linear based on the fact that it looks like it might be what?
Not a constant change.
We have a constant, here's what we do. When we write an equation to model the ordered pairs, we say, what do you have to do to x to get y? And you just told me what you have to do to y to get x. What do you have to do to x to get the y? You have to multiply by 3. You have to multiply, let's write that out. Multiply x by 3 to get y. We were doing this back a while ago. So in other words, we have a function rule here that will help us make an equation. Multiply the x value by 3. So y equals 3x. So it turns out that this one actually is linear because it meets all of the rules for being a linear equation. Anybody remember all the rules, all the things it has to pass, the test it has to pass? Not the vertical line, because that tests for a function. What tests for it to be linear? What's one thing, Katie?
They can't have like exponents.
They can't have exponents greater than, they have to have an exponent of what? I shouldn't say greater than 1. They have to be both taken to the first power. Are x and y both to the first power in our equation?
Yes.
Okay, give me another test it has to pass. Katie?
It can't be in like, I think it's the denominator.
They can't be in a denominator. Are either of them in a denominator? No. What else? There's more tests you've got to run through for it to be linear. X can't be multiplied by y. Are x and y being multiplied by each other? No. There's more tests. Kaden?
I think they have to be on like the same side.
To be in standard form, they have to be on the same side, but not to be linear, they don't. There's another thing they can't be in or under. Josh?
Radical sign.
They can't be under radical signs. Are either of them under a radical sign? No. One more thing. They can't be an exponent, so they can't be something taken to an x or y power. Is that the case here? No. So this is actually a linear relationship, even though the table kind of threw us off. And the problem is when the x's don't have a constant change, like ours didn't, we can't say that doesn't mean then it's not linear. It's if the x's have a constant change, do the y's have a constant change? That's how we check if we're going to use that method. Well, since we couldn't use that method, we instead run it through what can we do? Can we try and write an equation for what's going on here? And we could. And then we run it through the test of whether it's linear or not. So we are going to, and I meant, could you erase if you took up all this room like I just did? Because this is really supposed to be divided in down the middle here. We're going to be doing both A and B, so we're going to do it like this, okay? So multiply x by 3 to get y. So y equals 3x. We already decided it's linear. Now the real question is it direct variation? Does it represent direct variation? Is this direct variation? What's the direct variation form? Not standard form. What's direct variation form?
Y equals kx.
Y equals kx. Does this look like y equals kx?
Yes.
With k equals what?
3.
Yeah. So this is direct variation. We would say k is equal to 3, so it is direct variation. So method one, when you're asked to determine if it is direct variation or not, a table of ordered pairs, you can either find the function rule and write an equation, and then determine from the equation if it's direct variation, or tell me what would happen. Let's go up here in some white space up here. What would happen if I changed direct variation so that it was solved for k? How would we get that equation solved for k?
Divide by x.
Divide both sides by x. If we divided both sides of this equation by x, we would be able to say k is equal to And we would say k is equal to y over x. So in other words, if we can divide just the y value by the x value and get a constant, we know that we have direct variation. So let's check. We already know this one's direct variation, so let's check it out and see if, so k equals y over x. Can we get that to happen for every problem? Devin already said at the beginning of this, if you take each y value and divide by 3, you get the x value, right? 6 divided by 3 equals 2. No, we're supposed to divide by the x value. Sorry. We're supposed to divide by the x value. It's like we should get the same k value. The y value from the first ordered pair is 6. The x value is 2. 6 over 2 is 3. The next x or y value is 12. 12 over the x value for that ordered pair. X value is what? 4. 12 over 4 equals 3. That's 2 ordered pairs. It's got to work for all of them. 15. So if you use this method, you have to test it for all sets of ordered pairs, y over x. So now we have 15 over 5. What's that divide out to? 3. And our last one is 24 is our y value divided by its x value of 8. What does that equal? 3. So we would say there is a constant of variation. It is 3. So is direct variation. So right now you might be feeling like that's kind of redundant, like, yeah, we already knew that. But again, I'm showing you both ways that you can check for direct variation. You can either do the equation way, you write the equation, and then determine from that, or you check to see if there is a constant of variation. When you divide all the y's by their x, do you get the same number that you could call a k value? Okay, let's go to the second table here and see. Can you figure out what you do to x to get y this time? What do we do? I can already tell the x's aren't changing by a constant amount, so we can't check to see if it's linear that way. So, Andrew, what do you get?
X minus 3.
So subtract 3 from x?
Yeah.
Subtract 3 from x to get y. So y equals x minus 3. This is direct variation. What do you think? Is it y equals kx form? Because what can't happen when the y is by itself, y equals kx, what can't you have? You can't have anything being subtracted or added. We would say there is, you might be tempted to say there is a k value, and that k value is 1. That's cool, but that's like our shoe problem. Yes, there's a k value of 2. You multiply the number of people by 2 to get the number of shoes. But when I threw in that plus 4, remember, we said it's not direct variation anymore. So the plus 4 took it away from being direct variation. That 2 is no longer considered a k value at that point. So we would have to say this is not direct variation. And when it's not direct variation, we have to state that something has to do with the c value. So let's get this in standard form. What would we do to get that in standard form? How would that look? Y equals x minus 3 in standard form. Andrew?
Subtract x from both sides.
Okay, subtract x from both sides. So y subtract x equals what? Negative 3. Or negative x plus y equals negative 3, right? As long as the x's and the y's are together and the constant's on the other side, what's our c value? Negative 3. So c equals negative 3. That's our proof that it's not direct variation. We wrote an equation, we put it into standard form after we decided it was not direct variation so that we could say what our c value is. So that -3 is throwing the whole thing off. Well then, what should happen when we try to do k equals y over x? Or in other words, we take each of the x, y values and divide by their x's. Let's try it. So 5 over 8. What's that equal? Try it on your calculators. I already know what it is, but let's see. Let's actually divide it out so we know if we have direct variation or not.
0.65.
Okay, 0.625, 625 thousandths. Okay, what would our next ordered pair be that we're going to set up?
4.
4 over 7. I don't think this one's a nice decimal.
No, it's like 0.57.
Okay, let's round it to the nearest hundredth. What would the, or thousandth? Then we can see if it matches this one. 0. What? 571. Do we have a constant? Do we have a k value? No. We have one of them is 625 thousandths, the other one's approximately 571 thousandths. So we don't even have to go any further, do we? It's already broken down. We would say not direct variation. So if we use this method, once it breaks down, you gotta make sure you're setting up y's over x's though. Be careful, don't get caught. Make sure it's y over its corresponding x value. And then if once it breaks down, we say not direct variation because there is no k, let's just say this, let's say it this way. No constant of variation. In our notes anyway. No constant of variation. And we just proved it. We set up our relationships and divided them out. So again, when you're doing these in your homework, you choose which method you want to use. Do you want to describe what's happening to x to get the y? Some of you, you're not so bad at that. Others of you, that doesn't go so well. If that doesn't go so well for you, maybe you want to use method 2, where you set up all of the relationships of y over x, divide them out and see if you have a k value of constant of variation. And then you can determine if you have direct variation or not. Okay? Anybody have questions? Okay, then one other thing that we're going to do today is we're going to be able to write and solve direct variation equations. So if y varies directly with x. So right here, I want you to circle this. When they say it like this, they're not asking you if it does or doesn't. They're saying if y varies directly with x, they're basically saying it does. When you have a y that is varying directly with x, and then it says, and you are given at least one ordered pair. If you're given at least one ordered pair for the relationship, that's all it's going to take to help you be able to find the k value and write an equation. And then you can use that equation to solve for missing information. So, here's an example. Given that y equals 4 and 5/10 when x is 5/10, so in other words, here's our direct variation relationship. Right here. They're saying, here is a direct variation relationship where y varies directly as x. So what do we need to find from this? How could we find our k value? AJ?
So x is 10. We're trying to find one.
Right now, all I care about is the k value. That's all I want. I don't want any more than that. How would I find the k value, Shay?
4.5 over 0.
Yeah, remember, y over x gives us the k value. So we're going to put 4 and 5/10 over 5/10. Or in other words, it's kind of like saying how many 50 cents, how many times can you take 50 cents out of $4.50? We do not need a calculator. How many times can you take 50 cents out of $4.50? 9 times. So k equals 9. Okay, that gives us our k value. Now, what's that good for? We're going to write an equation. So we have our direct variation equation that has this model. We will sub in our k value and we will say, oh, here is the equation for this situation, y equals 9x, multiply the x values by 9, and you'll have the output y. Well, then it says find y when x equals 10. So we're going to say y equals 9x is our situation, our equation. Y equals 9 times 10. What's our y value?
90.
90. Does our answer seem reasonable?
Yeah.
Yes.
Why? Give me a reason why it seems reasonable. Convince me. Caden?
Because when you put 0.5 in for x, it went down to 4.5, and then when you put 10 in, it went up to 90.
Okay, when you put x in, when you put 0.5 in for x, it went down? I don't think I understand what you mean by it went down.
It was 9 before.
Okay, before we even knew though that it was 9, what about just this right here? This is our problem. How can we say that having a y value of 90 seems reasonable, considering that that's the information that we got in the beginning, Austin?
Because when x is 0.5, y is bigger than it, so if y is bigger than x.
Y was bigger than x in the given relationship. Y is bigger than x, so we better get an x value that is bigger, or a y value, excuse me, that is bigger than our x value of 10. And did we? Okay, so that part is at least reasonable. So, not saying that maybe we 100% have the correct answer. That doesn't guarantee that, is what I'm saying. It's saying, at least is my answer reasonable. What if, in this situation instead, they said, find x when the y value is 180. Find x when the y value is 180.
Then you'll divide by 9.
So then what would we be doing? So find, what if I gave you this problem? I said find x when y equals 180.
And we know that k is 9, so then it'd be, the equation would be,
We have our
equation
equation.
is 180 equals 9x.
Yeah, we have our equation that we set up, so we can use our equation to either solve for x or for y. We don't have to necessarily always be solving for y. We can also get our x values. So we would divide both sides by 9, and what's our x value? Does that seem reasonable?
Yes.
Because again, what was the case?
Y is bigger than x.
Y is supposed to be bigger than x, and we got an x value smaller than our y value, didn't we? So again, we can, once we set up the equation, what we have to really understand here is this is a situation that has a ton of ordered pairs. Here's one ordered pair right here. 0 and 5/10, 4 and 5/10. We just found another ordered pair over here. What's that ordered pair?
1090.
1090. We just found another ordered pair for this relationship right here. What is it? 2180. So in other words, all these ordered pairs are part of what relationship? Which direct variation relationship? How would we describe it as an equation? All of these ordered pairs come from what relationship? Give me the equation.
K equals 9.
Well, k does equal 9 in this situation, but that's not my equation for this.
Y equals 9x.
Y equals 9x. We need to understand that this right here represents any ordered pair in that relationship. It tells us what's going on. So when we have y equals 9x, that tells us we have that direct variation relationship. Because what's our c value for this one?
Or 0.
0. There's nothing being added to those x's. There's nothing being subtracted from those x's. If we move those x's over to the other side of the y, what would we have on the right side? If we took 9x away from both sides and put the x's over with the y, what would we have?
0.
We'd have 0. So, Again, we have to understand, how can we tell if we have direct variation or not? We take those away, we have 0. What's C supposed to equal in a direct variation? 0. Yes, C is supposed to equal 0, and it does. So we can say that we have direct variation. There's a variety of ways here that we're looking at it. Okay, let's get you started on your homework then. You don't have any graphing to do, so you don't need a handout from me.